In this lesson, we're going to be discussing integration by parts, which is obviously a technique of integration. Now, you've had a few different techniques of integration. One simple one was this one. You learned that this was equal to that, right? And effectively, that took advantage of the fact that we already knew that the derivative of x to the n is nx to the n minus 1. So basically every differentiation rule we've learned, you can reverse and write some sort of integration rule to account for that. So we've done things like the power rule, which I just did here. We reversed the chain rule via u substitution. And now what we're actually going to do is we're going to reverse the product rule. So I just want to recall the product rule first. The derivative of the product of two functions is the first function times the derivative of second plus the derivative of the first function times the second function. So again, that was first derivative of second, second derivative of first. All right, now what we're going to do is phrase this in terms of an integral instead. So if the derivative of this is this, then the integral of the right side of my equation should equal the left side. So I'm going to write that now. The integral, and I'll color code a little bit, the integral of f of x g prime of x plus f prime of x g of x, that all as one expression, that integral will equal the original function. And I guess we could say, plus a constant. So now what we're going to do is we're just going to split these two pieces of our integral. We're just going to add those two integrals together, and I should technically have, integral dx, so that we know what variable we're integrating with respect to. And if we isolate this integral, fg prime, we get the integral of f of x, g prime of x, is equal to f of x, g of x, minus the integral of f prime of x, g of x. So now at this point then, what we're saying is if we find things in this form, and again I need to have a dx in here, if we find things in that form, then what we can do to integrate them is just do this process instead. And you might say, well, how is that any simpler? Well, sometimes it's not, and then this technique is not appropriate. But the basic idea is that you're going to write it as a product of two functions minus some integral that is hopefully more doable. So let's write this a little more concisely, because that whole f of x, g of x, prime, all that stuff is a little bit more annoying to write. So the rule is a little bit more concisely written, something like this. The integral of u dv is equal to u times v minus the integral of v du. And we'll do an example, because obviously this is probably seeming a little bit esoteric at this point. So here's our first example. We'll do a few of them. The first one is x sine x. So this integral on its face is not really a simple looking integral, right? I mean, we've got a product of two functions, so we certainly wouldn't make the mistake of doing like x squared over 2 times negative cosine of x, because we know that we don't just do the derivative of that and the derivative of that. That's not cool at all. that would not respect the power rule differentiation. So what we will do though is we're trying again to write it in this form. So we kind of need to declare a u and a v value. And in this case, the y's value for u will be x. And for v, or I should say dv, will be sine x dx. And remember, we are totally changing our variable with which we are the variable with respect to, sorry, variable that we are integrating with respect to. So here we're with respect to v, and we end up with respect to u. So you can see this dv is just this expression, which means for v, you'll actually have to do a little quick antiderivative or integral in your head, and you'll see that that's actually negative cosine of x. And if you're wondering why isn't there a dx there, well, that's because when you take the derivative of v with respect to x, right, we get a dx over here. And then du would equal 1 dx. And so now we're going to use this and pick up with the rest of our question. So that integral is equal to u times v, that's x times negative cosine x, minus the integral of v dA. So v, that's negative cosine of x, so I'm going to make that positive cosine of x. Du is 1 dx. And you can see now, basically what we've done is we've said, well, that looks like part of our product rule. And again, we don't want to be robots about this, so try to keep in your head a more deep level of understanding. We're basically just taking these two parts of our product rule and saying, well, that kind of looks like one of the parts of a product rule. If we had sine is antiderivative is negative cosine, and x's, x's derivative is 1. So we can rewrite this to have basically a new iteration of our product rule. And now negative x cosine x, and we just anti-differentiate cosine of x, which is sine of x, plus c. And so if you take the derivative of this whole expression, you'll get x sine x. And yes, it would involve a product rule, but anyway, you'd end up with x sine x when you take the derivative of that. So our task will basically be now figuring out how we can construct u, dv, du, v in such a way that it actually makes a more simple integral. And I'm leaving my concise definition of the of integration by parts here. So now we're going to integrate this function, which is the natural log of x. So again, we need to declare u and dv, because that's where we start, right, in our integration by parts. The goal, though, is to end up with v du being simple. So in this case, maybe pause for a second and see if you can come up with a value that something u could be and something dv could be that would make this thing come out with a nice v du. Because uv is fine. We don't care about that. We don't even have to integrate it. It's just integrating v du that's the hard part. So think about that for a second. And hopefully you clicked pause and did that. A good choice would be u to be natural log of x and dv to be dx, which means du is 1 over x dx. And again, don't be a robot about why that dx is sitting there. Think about why it's 1 over x dx. Notation is really important in calculus. And then v will be, sorry, I lost my train of thought. Du. So dv was dx, then v is x. Oh, I know where I was going with this. Is I was trying to, I wanted to remember, to keep our eyes on the prize here with v du. And what we're staring at with v du right now, if you multiply v times du, the x in 1 over x will become a very simple integral. So let's see that right now. Again, this integral is now, via integration by parts, is equal to u times v, so that's x, natural log x, minus the integral of v du, so that's x times 1 over x dx. That's equal to x natural log x minus the integral of 1 dx, which is x natural log x minus x plus c. So that then is our antiderivative of the original expression. So if you took the derivative here and here, you have to do a little product rule, some simple calculations, you'd end up back with natural log of x. So something that, on its face again, the integral of natural log x, you're trying to think, what's the antiderivative of natural log x? Well, I don't know that. So integration by parts makes that easy. Sometimes, though, this v du, sometimes it's still awful. And we'll see one like that right now. So, the integral of x squared e to the x dx. And so we need to decide on a u value and a du value in this, and maybe pause here and think about what you would do. We're going to let u equal x squared, dv equal e to the x dx. So du will be 2x dx. V will be e to the x. That's kind of nice, right? But now when you look at v du, it's not exactly a super sweet integral. So again, here's our rule. And we'll take it from there. We'll just sort of see what happens. Kind of got a faint marker there. Again, it's u times v. That's x squared e to the x minus the integral of v du e to the x 2x dx. And actually, I'm going to move this 2 out here. This integral, though, now, e to the x dx, that even is going to involve yet another integration by parts. And that might not make you very happy. But it's kind of cool when you think about it. You'll see the end result here. So let's let u equal x and dv equal e to the x dx. Of course, v is going to be e to the x again, but du is now, 1 dx. So again, we rewrite our integral. That's x squared e to the x minus 2 of all these, u, v, x, e to the x, minus the integral of v du, which is 1 dx. And here I'm sure you can see that the rest of this will be pretty simple because the integral of e to the x is e to the x. So let me just give you a final answer here. X squared e to the x minus 2x e to the x. 2 So there you go. What we did there then was we effectively used an integration by parts, found e to the x times x dx, and thought to ourselves, the problem with this one was that it was x squared, and it didn't get rid of its x when we took its derivative. But with this one, if we let u equal x and dv equal e to the x again, we'll get our e to the x again, but our x will be gone. So when we take the derivative, we get 1, and then we're left with something that's very simple to anti-differentiate. Okay, thank you.